Pluto is a remote and perplexing diminutive dwarf planet that was once a part of our solar system's planetary group. However, later, amazing declarations by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a frightening revelation. They suggested that this icy world is on a potential crash course with Neptune. But how could this happen? And what might be the repercussions of such an enormous event? Are we witnessing a rare galactic phenomenon? Or is there something else to this impending cosmic conflict? Join us as we examine the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was renamed as a dwarf planet partly due to its unusual orbit, remains a subject of interest and research in the astronomical community. According to recent estimates by leading scientists, Pluto's trajectory is dangerously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku sounding the alarm about a potentially hazardous impact between these two planets that could present a significant threat to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike any other planet in our planetary system. It requires an astounding 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one complete revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating considerably from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit indeed intersects Neptune's. The stability of Pluto's orbit, despite these complexities, is a testament to the intricate dynamics of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem demonstrates how the paths of Neptune and the Sun's gravity all interact in a complex manner. The terms libration and latitudinal libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's located at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from intersecting. Latitudinal libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's positioned significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, von Zeipel, Kozai, and Litov, who studied how things move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unusual. Even though Pluto's trajectory seems unpredictable, this oscillation helps keep it moving smoothly for a long time. The VZK oscillation shows that even if things in space seem chaotic and random, some patterns and rules keep everything in order. These factors help maintain Pluto's orbital stability, ensuring it doesn't collide with Neptune or get off course. This three-body problem aids in understanding how these elements change due to the way these space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, distant worlds, and their stars. Numerical simulations in the late 1980s revealed that, Despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to huge differences over millions of years. However, these extraordinary properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This association helps keep Pluto's way consistent. However, Neptune isn't the only one to focus on. Jupiter's gravity likewise plays a critical role in keeping Pluto's orbit protected and stable, and Saturn helps as well. Altogether, these tests show that Jupiter's gravity alone is sufficient to ensure Pluto remains on a steady path for seemingly forever, even billions of years. So, it seems like Neptune, Jupiter, and Saturn are cooperating to ensure Pluto continues to move safely in space without experiencing trouble. These peculiarities are fundamental in the context of the universe for maintaining the order and consistency of celestial bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially crash into others or be ejected from their stable paths, leading to a cascading effect on other celestial bodies. For Pluto, particularly with discussions about it possibly crashing into Neptune in the future, understanding its orbit is really important. This gives a clearer picture of the solar system's dynamic nature. The position of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using computer simulations has been very helpful for scientists to figure out how Pluto moves in space. These simulations use complex math to imitate how Pluto and other space objects, like Neptune, pull on one another. By changing little details in the simulations, astronomers can see how even minor changes can have a big impact on where Pluto ends up. In the late 1980s, these simulations revealed something quite intriguing about Pluto's path. Even though it has factors like an inclination and a latitude libration to keep it steady, its orbit can still be quite wild and unpredictable. If you start off with just a tiny difference in where Pluto is or how fast it's moving, over many years its path can end up looking very different. But even with this chaos, Pluto's orbit remains stable for an incredibly long period of time, like billions of years. This means Pluto's journey around the Sun has a sort of order to it, even though it seems out of control at first. Predicting cosmic events, especially when they involve chaotic orbits like Pluto's, poses huge challenges. The inherent unpredictability of these systems means that long-term predictions are often fraught with uncertainties. While numerical simulations provide a solid means to understand and anticipate the future paths of celestial bodies, they also highlight the limitations in our predictive abilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor error or misrepresentation can lead to vastly different outcomes, making precise predictions a daunting task. Besides, the turbulent nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us how our knowledge about the universe still remains limited. Grasping the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So, why are significant astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, regardless of this large number of perplexing powers attempting to keep such an occasion from happening? Neil deGrasse Tyson, an unmistakable astrophysicist and a critical promoter of cosmology, gives an extraordinary point of view on the mysteries of our planetary group, especially the captivating instance of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful analysis on the evolving nature of celestial mechanics and the public's interest in the unexplored realms of space. Tyson's position on Pluto's renaming is grounded in the ever-expanding knowledge of our local planetary group. He views the renaming not as a downgrade, but rather as a vital adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The fascination with these questions, particularly the possible interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our planetary group. His work emphasizes that the more we unveil about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another prestigious physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often unusual forces that shape our universe. Kaku is known for his ability to bridge complex scientific concepts with futuristic visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's views on Pluto and its orbit emphasize the need for ongoing observation and advanced modeling to anticipate and understand potential cosmic events. He sees the interactions between celestial bodies as a crucial area of study, not only for academic interest but for practical implications. The potential collision between Pluto and Neptune, for instance, is not just a hypothetical scenario, but a reminder of the dynamic and often chaotic nature of space. Kaku's futurist perspective urges us to consider the broader ramifications of such events, from the impact on our understanding of the local planetary group to the potential need for future space interventions. His viewpoint underscores the importance of being prepared for the unexpected in space. His work suggests that the more we comprehend the forces at play, the better equipped we will be to navigate and possibly mitigate the effects of cosmic events. Both Tyson and Kaku's perspectives converge on the idea that space is a realm of perpetual discovery, and that our current understanding, while vast, is still limited. Their emphasis on the need for constant exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are now, but also anticipating how they might change in the future. The potential impact scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for robust scientific inquiry, advanced technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to continue pushing the boundaries of our knowledge. There is a general scientific consensus that, for the foreseeable future, the orbits of Pluto and Neptune remain stable due to their mean motion resonance and the various gravitational influences acting on them. Thus, a direct collision between Pluto and Neptune is highly unlikely. However, the intricacies and potential perturbations in orbital dynamics mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behaviors and any potential risks they might pose. While the scenario of a Pluto-Neptune collision is largely speculative and considered improbable with current understanding, it highlights the importance of continuous research and observation in cosmology. Advances in technology, including improved telescopes and virtual simulations, will help astronomers refine their models and predictions, ensuring that we remain informed about the dynamic and ever-changing nature of our local planetary group. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the erratic nature of celestial mechanics both underscore the need for continuous exploration and a flexible understanding of our universe. The potential impact scenario, while highlighting the dynamic and complex interactions within our planetary group, ultimately reminds us of the vast, still unknown areas in our comprehension of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe.